So thank you to the organizers for the invitation, and you know, it's great to be here, and this is the first time we're giving a two-part talk, so we'll see how this goes. But hopefully I can give you some idea of, you know, what really goes into the analysis behind these estimates, and hopefully by the end of the talk you'll see that it's really quite simple, and we're giving away all the secrets, as I guess. I don't know. Okay, so let me remind you that the way this sort of started was you asked the question, what does an eigenfunction look like which saturates this Hörmander bound? So I guess I should remind you again what the Hörmander bound is, right? And it's just that that the L infinity norm of the eigenfunction is bounded by h to the 1 minus n over 2. Right, and so we're asking ourselves, what does an eigenfunction look like if it saturates this bound? And sort of everybody who's in the business believes that it looks like a zonal harmonic, right? Everybody who sort of has thought about this much believes it looks like a zonal harmonic. And I'm going to remind you again about this idea that eigenfunctions should decompose into geodesic beams, and Steve is already giving me the stink eye about our terminology, but that's the way it goes. So we have these geodesic beams, which I remind you are functions which are localized at scale h1/2 around a geodesic, so transverse to a geodesic. Their profile should be L2 normalized, and so that's why in 2 dimensions we have this h to the minus a quarter here. And along a geodesic, they should oscillate at frequency h inverse. So more, roughly speaking, they're solutions of the Helmholtz problem, right? They're solutions of minus h squared Laplacian minus 1 is u is 0. And so eigenfunctions can really be decomposed into linear combinations of these things, at least locally. And so we asked ourselves, as Scheisse described, how do you make an eigenfunction out of geodesic beams which saturates the L infinity norm? And I remind you, I know you saw this, I don't know what, an hour ago.
But then we had coffee.
Yeah. So I remind you that you first ask yourself, okay, well, I need some mass, I need some L infinity norm, so there'd better be at least one beam through this point, right? And again, when you put one beam through this point, I've L2 normalized these things, and so you get this h to the minus 1/4 growth in the L infinity norm, right? And you say to yourself, well, that's not very good. I haven't done very well. I'm way below this Hörmander bound, and so you ask yourself, how do I make it bigger? And there's only one thing to do. If there's only one thing to do, you put another one through, right? You put another one through, and now you realize that something good has happened. This L infinity norm has increased more than the L2 norm, just like Scheisse says. And so you do it again, and you're happy because it works again. And you keep doing this until you become unhappy. And the answer is you can't do this once you've put h to the minus 1/2 of them through this point. Right? And at that stage, because you've sort of filled up all the directions with things, with geodesic beams of the same mass, and you realize that when you L2 normalize this function, the sum of geodesic beams, you saturate the Hörmander bound at this point. And again, I would just want to stress that, in fact, on the sphere, you can quite literally build a zonal harmonic this way. You can write it as a sum of in that case, highest weight spherical harmonics. Okay, and so if you think this way, you want to be able to say that this really was the only thing I could have done. Right? That really, in each direction, I should have essentially uniform energy. Right? And this is where somehow we started now, I guess, a couple of years ago. And the idea was, okay, so we didn't quite have this picture in mind. This was not so clear at the time, but we wanted to know, what is the defect measure of an eigenfunction which saturates the L infinity norm? And so I should remind you, what is a defect measure? I mean, nobody's done that yet this conference, so I guess that falls to me. And so what is it? It's a measure which tells you about concentration in phase space, L2 concentration in phase space. And it's just defined as follows. Right? I have some sequence of functions, and it's a radon measure which has the property that when I apply the quantization of an observable to u and pair it with u, this converges as h goes to 0 to some integral against this measure. And I remind you, I mean, we all, this is a microlocal conference, so we all know this, but I remind you that this mu is nothing but sort of the energy or the square of the L2 mass placed at position x and momentum c. Right? And the way to see that is just, okay, well, what does this quantization do? It multiplies the piece of u at position x and momentum c by a of x c, and then I sort of conjugate away the oscillation. And so if you believe that that's what this quantization is doing, it's natural that this mu is telling you about how much energy there is at position x and momentum c. And just for an example, if we have the sort of standard coherent state, which is again a Gaussian at position x naught, and this is a one-dimensional example. So it's a Gaussian at scale h1/2 at x naught, and it's multiplied by a plane wave oscillating at frequency c0 over h, or in other words, momentum c0, and it's L2 normalized. And okay, you can all check, or maybe Jesse's child can check, that by stationary phase, the defect measure is this delta mass at position x naught and momentum c naught. Okay, and so right, you can just look at this function and see, okay, all of the mass is really at position x naught, all of the mass is really at momentum c naught. So this is making sense. This is really telling me about where the energy is. And then there are a few facts that that you should know about defect measures, right? One is that, and concerning solutions to my equation. So for me, P is going to be the Helmholtz operator, but again, as Shiza mentioned, all of this works when P is a much more general pseudodifferential operator. And you know that if P solves this equation, then first of all, this defect measure is supported on the energy surface, right? It's supported on the energy surface, in this case, S star m. And so that sort of jives with our quantum classical correspondence idea, because this is just the quantization of momentum squared minus 1. So I'm living where that Hamiltonian has 0 energy. Okay, and moreover, these defect measures are invariant under the geodesic flow. And that's sort of going to be, that's a crucial fact. And it's illustrated, if you want, by Egerov's theorem, but there are other ways to see that. And the point is that now we see the quantum classical correspondence, right? We see that this measure, it's supported on the energy surface, and it has a certain invariance under the classical flow. So these pictures that Shiza showed you of billiards and their corresponding eigenfunctions sort of make sense in this context. You see the effect of the geodesic flow. And so again, we think to ourselves, now we have this tool of the defect measure, which tells me about where the energy is in phase space. We have this idea that from geodesic beams that the energy should be uniformly distributed in direction. And we ask ourselves, what does the defect measure of an eigenfunction which saturates the L infinity norm look like? And again, there are two ways to think of it. It should be like a zonal harmonic. And so again, a zonal harmonic has defect measure, which is just the volume on the flow out of the cosphere bundle over a point. It's just the volume like that. And so that's the enemy. Another way to think about that is that it has uniform energy in direction. It has uniform energy in direction, and that's what we were describing on the very first slide. And so how do you want to think about this defect measure? Well, you want to take somehow the piece of it which looks like the zonal harmonic. And the way we're going to do that is we're going to assume we have some defect measure, right? Again, telling you about how much energy or mass there is in certain points in phase space. You're going to take the subset, some subset of directions over your point, right? Any subset of directions over your point, and you're going to find somehow a directional energy density. And the way you do that is you take this subset of directions, you flow it out forwards and backwards in time for some time delta. So this gives you a little slab of geodesics, and a little slab of geodesics. You take the energy there, and you average, right? And the point is, this is doesn't depend on delta, right? It doesn't depend on delta, and that's because mu is invariant under the geodesic flow. So at least when delta is small, this is okay. And it really is telling you how much energy there is in each direction, right? You can't, I should point out that you can't, of course, just take the energy of this subset. That'll just be 0, right, because it's transverse to the flow. So you have to do something like taking some density. Otherwise, you're out of luck. OK, so this is telling you about how much energy there is in each direction, right? How much energy there is in each direction. And we learned, or we think, that the enemy is the uniform measure, right? The enemy is the uniform measure, and that's because a zonal harmonic has that uniform defect measure. So for the zonal harmonic, this f is just 1. Or another way of saying that, again, is that the energy should be uniform in direction. Right, and so the way you want to think about taking the piece of this measure, which is looking like the zonal harmonic, is just take the Radon-Nikodym derivative, right? Take the sort of Radon-Nikodym decomposition of this directional energy density. That gives you some f, right, which is what you should think of as the piece of this measure, which is uniformly distributed, or effectively uniformly distributed in direction. Okay, and it's this f, therefore, that should come up in any estimates we have on the L infinity norm. And indeed it does. Okay, so the sort of starting point for all of this stuff was well, okay, there was some work with John Toth about eigenfunctions concentrating on single geodesics, but the starting point for this technology is here, is that you describe the defect measure of an eigenfunction saturating the L infinity norm in this way. Right? I know that the value at a point is controlled by some universal constant times the Hörmander bound times this integral of the square root of f, times the integral of the square root of the piece which looks like a zonal harmonic. And again, I remind you, well, a couple of things. If this f is 0, of course, you have sup norm improvement, right? You have little o improvement. And the zonal harmonic has f is identically 1, right? So this is really showing you that in a certain sense, your eigenfunction needs to look like a zonal harmonic. And this statement alone can be used to recover sort of all of the little o improvements that are available for sup norms. And the reason is that this square root of f dvol, is invariant, an L2 function which is invariant under the first return map. Right? And so Sog and Zeldich have a theorem which says that if there are no such functions, then you get a little o improvement in the analytic case, and this generalizes that to the smooth case. And then from there you get all of this recurrence statement, all of this looping statement, and so on. But this is where the story starts. You can say that a defect measure of a saturating eigenfunction is the same as that of a zonal harmonic. And then, as Shiza said, sort of she and John Toth were working on averages, and we sort of somehow got together. It was anyway. And then we wrote some paper with John, but the sort of the realization that this was the same story as for that averages are the same as L infinity norms happened a little later just with Shiza. And so you have exactly the same theorem, and hopefully this, okay, yes. You have exactly the same theorem now, except for instead of a point, you have a submanifold. Right? And so I've done, okay, this is the same slide, except that everywhere there was an x, there's an h, and there's a k instead of an n. Right? So it says that for an average, again, the defect measure looks like the natural enemy. Whatever the natural enemy is, I won't belabor that too much, but it looks like the natural enemy. Okay, so why is this working, right? So I promised you some idea of really what's going on in the background here. And so we want to describe concentration of eigenfunctions which saturate L infinity norms, saturate averages. And so where does this start? Where does this start? And there's this simple fact that, okay, it was new to me at the time. I don't know if it's, whatever. That concentration in frequency implies improved L infinity estimates. And that's really the story. So I'm going to imagine I have some function in Rn, UH, which is localized to frequency xi0. And then if you just multiply it by some oscillating factor, this will now be localized to frequency 0, right? This will be localized to frequency 0. So that's not news to anyone, but there you have it. So, and my real assumption from the beginning is, okay, imagine that the defect measure for this u is supported where xi minus xi naught is smaller than some r. Well, then the defect measure for this red function is, of course, supported in frequencies less than r. And now you should ask yourself, what does that do for me, right? Why is that good? How does that improve L infinity estimates? And the answer is that if I think about a derivative of this red function, it's better than you might think, right? It's better than you might think, and in particular, it's better by this factor r. And the way to see this is that, okay, if I move this h over here, then this is just a pseudo-differential operator with symbol xi. And then the so on the support of this measure, that xi is bounded by r. That gives me this extra r here. Right, and of course I can iterate this. Right, I can take many derivatives. If I take n derivatives, I'll gain r to the n and lose h to the minus n. Right, so this is better than sort of the standard estimate for some compactly microlocalized function exactly by this r, this power of r. And okay, so now I have estimates on derivatives. What's the thing I can do to get L infinity norms? Just use the Sobolev embedding. There's nothing more you can do here. And so you use the Sobolev embedding. It takes you n over 2 derivatives, right? And so instead of h to the minus n over 2, which is the standard Sobolev estimate, you get rh to the minus rh inverse to the n over 2. Right, so you have this improvement by r. This localization in frequency gave you an improvement of r. And now, okay, so Shaiza already mentioned this, but if I'm really thinking about defect measures, I'll always have these annoying little O of 1, errors, right? There's nothing you can do about that. And so if you want to get quantitative improvements, you need to think more sort of finely than defect measures. But you'll notice that these statements are really, you know, fairly rough, right? This is just a statement about where is the function living. And we know how to say where a function lives in a much finer way, and that's the wavefront set, which we'll see in a second. But here I'm just going to talk about the support of the semi-classical Fourier transform, which again, roughly, is the wavefront set. So I'm going to tell you the same story now, but okay, the support of the semi-classical Fourier transform is now supported at frequency xi0 up to scale r. If you remove this oscillation, this red function is supported at frequency xi less than r. Can do exactly the same thing. The only difference is now I don't have these annoying errors, and I can use the Sobolev embedding. Okay, and so here on the right-hand side, I'm sort of forced to take r not going to 0 with h, because if it does, then this error will swamp out any gain I have. But on the left-hand side, I can start to take r's which are depending on h, r's which are which are going to 0 polynomially in h. Right? And so I can get polynomial improved estimates for each of these concentrated states. Okay, so this is the story if I really have a function which is localized at some frequency xi naught in n dimensions. But we need to, of course, upgrade that if we want to say something about eigenfunctions, because we're not likely to get that kind of localization. We're likely to get localization near a geodesic. And so what I'm going to do is I'm going to imagine that now I have a function which is localized near some geodesic. And my coordinates are t along, okay, that's a t, but anyway, it's very small. And s orthogonal to the geodesic, right? And I'm saying that I'm living inside this little tube of radius r. Okay, and what you can do is you can remove all the oscillation in the s variable. And exactly the same way, right? You just multiply by some oscillating factor to remove the oscillation in the s variable. Okay, and so again, let me tell you the story with measures, right? So the story with measures is now that I'm supported in this tube, right? of radius r around the geodesic. So if I look at this red function, the support of its measure is in cs less than r, so just in the s variables. And again, so now if I differentiate in s, because I know what the symbol of this operator is, I get this gain of r. I can do this as many times as I like, and I can use the Sobolev embedding. Okay, so when you do that, right, you're doing the Sobolev embedding now in one fewer variables. So you get this h to the 1 minus n over 2, and you get this gain of r to the 1 minus, or r to the n minus 1 over 2. And of course, if I'm thinking about measures, I have this loss. Okay, and we'll deal with this L infinity to later. All right, we'll deal with that later. But this concentration story is telling you that if I'm concentrated, I don't have as bad estimates as you think, or as you might believe. And again, you can do the same story now with the wavefront set. But the wavefront set is much finer. It won't have these little O of 1 errors. Okay, they would be h infinity errors, but I'll just treat that as 0. Okay, so again, the wavefront set now of this function, it's supported in this little tube. I remove the s oscillations to get something supported near 0. I can apply derivatives, and I get exactly the same story, right? Each derivative gives me RH inverse. I apply n over 2 of those, or n minus 1 over 2 of those derivatives, and I get the estimate I want. I get that this L infinity norm is controlled by, okay, the Hormander exponent, h to the 1 minus n over 2, times r to the n minus 1 over 2, times u in L infinity t L2s, right? So this is really actually the whole thing somehow, is that this concentration gives you improved estimates, okay? And now, so we need to know what is a geodesic beam? How do I think of it as a microlocal cutoff? And why is it a geodesic, right? Why should it be a geodesic beam, not some other random tube? Okay, so I want to think of these as microlocal cutoffs. And so I want to think of them as being localized to some tube, right? Their wavefront set should be contained in some tube. And what does that mean about the cutoff? Well, it just means that the support should be contained in that tube, right? There's nothing too surprising. But if I apply something, some microlocal cutoff like this to a function, it will be localized now in the sense of wavefront set to a tube. Okay, why a geodesic tube in particular? Why a bicharacteristic tube? And the answer is again, it should respect the equation, right? It should respect the equation. If it doesn't respect the equation, then when I apply this cutoff, something bad will happen to me, right? I'll get something which is only big O of h, not something, say, very close to 0. And all right, I should not lie to you quite this much here. We're only going to ask this to be true near the point we're interested in, right? If you try to do this globally, then you have a global problem and you need to worry about what's happening with the geodesics. But if you only worry about solving this equation sort of near a point you're interested in or near a submanifold you're interested in, then you don't care about the global structure of the manifold. Okay, so what does this mean? This means that, of course, the commutator should be small. And that's the same thing as saying that HP chi tj should be 0, right? I mean, plus some extra stuff, but certainly the symbol should satisfy this transport equation. Right? And so now I have a function which is localized in a tube, and it should be, well, invariant under the geodesic flow. So the only tubes that can do that are geodesic tubes, right? And now there I am, I'm stuck. Okay, so now I know what these cutoffs should be, right? And that's a geodesic beam, right? Okay, so it's a beam, it's localized at some scale, in this case, scale r, right? So allowing a geodesic, and it's oscillating still at frequency h inverse, right? It's oscillating at frequency h inverse precisely because it solves this equation, right? And so now I know how to build these geodesic beams out of microlocal cutoffs applied to this function. Okay, so that's the first step. Now I can take any function, I can reconstruct it out of, or I can find geodesic beams from it. So the next thing I need to do is I need to be able to actually build the function. So I need to find enough of these tubes that I can cover the manifold, right? And so what I'm going to do is I'm just going to take some transversal to the flow, right? And I'm going to cover this transversal to the flow by some kind of good balls, right? Okay, these, maybe you can see the green. I don't know, it's pretty small in the back, but I cover this, this red set by some balls, and I build a partition on those balls. Those balls will be of small radius, of radius r. Right? And that you know how to do, we all know how to do. And then the question is, now I want to build a partition which is reasonable and which is living on these tubes. And well, the answer is I just solve some transport equation, right? I just solve HP chi tj is 0. Right? And then I get cutoffs to these tubes. And you'll notice that I said a good set of balls. Right? You don't want to just take any family of balls, because then you might cover this hypersurface too many times. Right? You want to make sure that they're sort of a reasonable cover, namely that for any r, each point is contained in only a uniformly bounded number of balls. There's some uniform constant which controls this. I mean, the estimates we prove will be true even if you don't have that, but they're not very useful. Right? You want to be able to really say that the number of tubes is telling you about the volume of this set in H. Okay, but now we're in a position to really decompose the function near a point. Right? We have, or near some transversal hypersurface. And we can do that exactly by taking this chi tj, right? It's a cover near this hypersurface. And so we can write the function as a sum of chi tj's like that. So again, I remind you that the theorem, the replacement for this defect measure theorem looks like this, right? We estimate we estimate the L infinity norm in some ball around a point by the Hormander bound, improved by this factor of r to the n minus 1 over 2, but multiplied by a gigantic sum, right? It's a big sum. It has, in principle, it has r to the minus n minus 1, or r to the minus n plus 1 terms in it. Okay? But that turns out to be very useful. Okay, so how do we get this estimate? Well, we decompose our function. We learned how to write a nice partition of a phase space into these tubes, so I can decompose my function, at least near this point, into these tubes. Okay, we learned that this chi tj is localized r close to some geodesic gamma j. We learned that localization to some tube like this gives you, there's some leftover lambdas. Okay, it gives you improved estimates, right? In particular, the L infinity norm of one of these tubes is improved by r to the n minus 1 over 2, right? And now the only thing I need to do is get rid of this L infinity in time, right? The only thing I need to do is get rid of this L infinity in time. And here's where we use the fact that this thing still solves the equation, right? Still solves the equation. In particular, I can control this L infinity in time by an energy estimate, right? I just have the L2 mass of the function plus H inverse times the operator applied to the function, right? And that allows you to get rid of this L infinity in time for sort of no cost. And I also want to point out that, of course, I mean, as many of us know, this is really just another statement that concentration gives you improved L infinity estimates, right? This is saying concentration H close to the energy surface gives you improved L infinity estimates, uniformly bounded L infinity estimates, right? But once you do that, you just apply the triangle inequality, and this is what you have, right? And this is what you have. Okay, so now we're in a position, again, where we can describe the structure of any eigenfunction which saturates the Hormander bound. If you sort of apply Cauchy-Schwarz in the right way, you can indeed see that each of these tubes needs to have, or a full measure set of these tubes should have a uniform mass. And it should be the maximal possible mass somehow for that to happen. And that's precisely the story on a zonal harmonic, right? You can, another thing I should point out is that if you take these r's to be H independent but small, then you recover the defect measure statement. Okay, so that's really what's happening. Concentration is implying improved estimates, and then you just decompose your function. All right, and now we want to get some dynamical improvements. And the way we do that is just Agarov's theorem. Okay, so I'm not going to be extremely precise about the times involved here. Just know they're like log h inverse, but a small constant times log h inverse in principle. And what you know is that if you take some quantization of an observable, conjugate by the unitary flow, you get a new observable just translated by the geodesic flow, right? And if I write that for an eigenfunction, right, I can rewrite this pairing as just an average over the flow, right? So this is not news. I mean, this is sort of standard now in the business. And now you ask yourself, what happens if the support of A has some non-looping property, right? So in particular, what I mean by this T0 non-self looping is that if I'm going to get the sign of T wrong, but this should be empty. Support of A intersect, I think it's phi minus T of support of A, but I won't vouch for that. This set should be empty. This is what it means to be little t0, capital T0, non-self looping. And if that's the case, then you ask yourself, okay, well, how big is this function, right? How big is this function? And the answer is, well, it's bounded by a constant times T0. And this constant, okay, the sup norm of A, if you want, goes here. And that's because basically this integral can just be replaced by the integral from 0 to T0, right? Because it never sees itself again. It never adds it up. And so that symbol now is bounded by a constant times T0. And immediately that tells you that this dual pairing, or this pairing rather, is controlled by a constant times little t0 over capital, okay, this should be a capital T0 times the L2 norm of phi. All right, so that's where non-self looping comes in. It allows you to understand sort of how much energy there can be on the support of A, how much mass there can be on the support of A. And now we need to pass from this estimate, this nice microlocal description of what an eigenfunction can look like if it has large L infinity norm, to an estimate which is purely dynamical. That's sort of the next goal. And then Shiza gave you a picture for how to do this, and now we're sort of really going to do it. And again, it's going to turn out to be relatively simple, right? Again, I'm going to I keep in mind that if I have a non-self looping symbol, then I get this estimate on the mass. And so I start with the estimate we had before, right? Just I've moved the HR inverse to the other side because otherwise I ran out of space on the slide. But anyway, it's on the other side, but it's the same. Okay, and now I need to understand a good way to control this big sum. Remember, this is in principle a huge sum of terms, right? There are an polynomial in h growing number of terms. So you can't just sort of stare at it and say, okay, it's bounded. That's not going to work out. You need to do something. You need to do something more, and you want to do something which removes the sort of specifics of the eigenfunction from the question and puts only purely dynamical assumptions in. Right? So what I'm going to do is I'm going to, I'm going to break the sets of tubes into a bunch of sub-collections. Right? So I just rewrite all of these tubes as a union over sub-collections GL. And the property that the GL will have is that if I take the union over J and GL, the union of the tubes there, then that should be TL, capital TL non-self looping. Right? And so what I'm going to do is I'm just going to apply Cauchy-Schwarz now. Right? And I'm going to do it in a sort of slightly non-trivial way, which is that I put in this TL over little tl, and I get this corresponding factor over here. Right? But it's Cauchy-Schwarz with just one. Okay, and now I want to use this non-self looping assumption, right? And so I rewrite this L2 norm as an energy on a certain set. And now I can apply Agarov's theorem, right? Because this pseudo-differential operator here is living in a non-self looping set. So I can just apply this estimate directly to see that this is controlled by the L2 norm of phi. And so now I have a purely dynamical statement. I have something which tells me that if I want to know about the L infinity norm in some ball, all I need to know about is the structure of non-self looping sets near the point x. Okay, so let me try to unpack that a little bit again. Right, so I just rewrite this. So here's the estimate. Again, we have this Hormander exponent improved by sort of the volume of the tube, which I'll remind you in a second, times the number of tubes in each non-self-looping set divided by their relevant non-self-looping time. Okay, and I remind you that the volume of this thing, the volume of this tube intersected with s star xm is r to the n minus 1. So you should think of this r to the n minus 1 over 2 as just the square root of the volume. Right, and so what this becomes is just that the L infinity norm is controlled by, again, the right power of h times the volume of each GL to the 1/2 times TL to the 1/2. And so, okay, what does this mean, right? This is a little bit complicated. It's more complicated than what Shiza showed you, which was just when you have one L, basically, right? And the answer is this is a recurrence statement. So why is this a recurrence statement? It's a recurrence statement because, well, okay, the first thing you do is you say, okay, imagine I have just two L's, right? A bad set and a good set, which is what Shiza said. And then you say, okay, well, the bad set can do anything. It can be self-looping after time 1. I don't have a problem with that. And the good set, as long as it's, doesn't see itself, I'm happy, right? This is the situation where you don't have loops coming back through X. But you can do more, right? You can say, okay, well, maybe I do have a lot of loops coming back through X. But maybe they're not close to being closed, right? And if you can do that, what happens is, okay, I start with this bad set, which is maybe consisting of all the closed trajectories. And then I have the things which are not closed. And I split them somehow. There's some way of splitting them so that I get, say, two sets which only see the other one, right? And you can iterate this procedure. But there's a price to pay. There's a price to pay because as it's sort of a priori better to have big volumes here. And that's because of this square root. Right, so there's some kind of quantitative recurrence going on, which is that if I need to be able to make this TL much bigger when I make the sets smaller. Okay? And so just as an aside, you can really show that if I take these GLs to be H independent, then if I have zero volume recurrence set, then I can make this thing as small as I want. Okay, so you can go back to this dynamical recurrence if you want. Okay, and I'd really like to know when you can make this as small as you want. What is the right dynamical condition, right? So I know, and I'll just point out that if you have a positive volume of closed trajectories, that you can't make this as small as you want. If you have zero volume recurrent points, you can make this as small as you want, but where does it live in the middle? I don't know. Okay, so now let's try to remind ourselves all of these situations where we had logarithmic improvements, right? We had logarithmic improvements in a bunch of cases, in Nonself flow, no conjugate points, non-positive curvature, et cetera, et cetera. And I'm going to try to explain at least what's going on in the background here. Like, how do you construct these covers? So Shiza explained one thing, which was if I have no conjugate points, and I have this if I have non-uniformly maximal self-conjugacy, then how do I get a cover? I'm going to explain some slightly different ideas for how you can use the dynamics to get a cover. And so to do this, I need to remind you about what an Ananassa flow looks like, right? And what it has is it has the stable and unstable bundles, right? And that's going to be the crucial thing here. And so the stable bundle is just sort of some vectors which contract forward in time, right? So if I vary in the stable direction somehow, if I go forward in time for a long time, they basically end up in the same point. And if I have the other direction, the unstable direction, it does the same thing but backwards in time. And I feel compelled to, I don't know, Maciek has this dance and Simon does it, so I feel like I have to do it. So the stable bundle is this one, right? It's contracting forward in time. And the unstable bundle is doing the opposite thing, backward in time. Right? So now I've done it. There we are. Okay, so what does this mean for constructing covers? Okay, so I want to, oh, that was not supposed to happen. There we go. I want to imagine that I have some tangent vector, some green tangent vector to the conormal bundle to H. Sorry, this should be unit conormal bundle to H, actually, but it should be tangent to the unit conormal bundle to H. And I want to watch what happens to it as I flow forwards in time, right? I watch what happens to it. And so this is sort of a generic vector. It's living somewhere between E plus and E minus. It's not in one of them. And so when you go forward in time, right, what happens? Well, the E plus direction contracts, the E minus direction expands, and you end up basically in the unstable direction. Okay, and you can, of course, do the same thing backwards in time, right? If you start with a generic vector and go backwards in time, you end up in the stable direction. Okay, now, so maybe, actually, maybe I will attempt to sort of augment the picture with drawing. So here I have the stable direction, right? And then I have the unstable direction, which is doing the opposite thing. Right, and I have some vector, which is the tangent space to Sn star H. Right, and you imagine to yourself that so this is E plus, E minus. And now you imagine that that you have some geodesic here which is essentially self-looping, right? It comes back to the conormal bundle, and it's sort of essentially self-looping. And now what happens? Well, if I can vary in this direction, right? I can vary in this direction because this is a direction in my tangent space. And what will happen? Well, after a long time, it will vary in this unstable direction. If I flow it forward in time, it will be turned into varying in the unstable direction. So if that direction is no longer tangent to my submanifold, then I can construct non-self-looping sets, right? Because again, if I sort of vary in this orange direction, or in this picture, the green direction, and I wait a long time, I'll be varying in the unstable direction. And so if when I look over here, right, my manifold is not in the stable direction, then I will miss the submanifold, right? And so then I can draw, oh, maybe I even have good, I have green chalk, excellent, on a green board. Right, so then I can come here and I can say, well, as long as I vary in this direction, everything is nice. Right, and so you get this sort of same picture that Shiza had, where this region is good and this region is potentially bad. Right? And okay, so at this point, I'm really talking still about non-looping, but let me tell you what this really says. Right, what this says is that if you take a submanifold in your manifold, and you look at, again, sorry, this should be Sn star H, I apologize. If I look at the intersection of the tangent space to Sn star H with the stable and unstable bundles, and call them n plus and n minus, then I say I have the splitting set, which is the set where this tangent space is a direct sum. Right? I mean, it's just a sum of stable and unstable directions. There's nothing in the middle, right? It doesn't have vectors like this. Or if it does, it has all of the intervening vectors. Okay, so if this splitting set is empty, then you're in business. You can construct a cover. Now, this is really still only using non-looping, not non-recurrence. And so there's actually something more which happens here, which is contraction. All right, so now, okay, sorry, let me go back. I can imagine that I have this splitting, but one of these factors is 0. Okay? So what's going on then? Then I have a new phenomena, right? I have a new phenomena, which is that when I go forwards in time, I'm going this direction, so everything is contracting, right? So you sort of can take a piece of your conormal bundle and float forward in time and get something like this, right? It will contract backwards in time. And what can you do in that case? Well, what you want to do is you want to sort of remove self-loops, right? And so you do the most sort of naive thing you could possibly do. You just grab the whole set. You grab the whole conormal bundle, flow it forward in time for a long time. It will contract, right? and you just look every single time it intersects the conormal bundle again, you say, okay, I get rid of those points. Right? I get rid of those points. So I start with the whole conormal bundle, and every time I come back, I remove those points. Okay, so that's good. Now I've constructed a non-self-looping set. But I didn't cover the whole manifold, right? So I've thrown some things away, and so I start this process over, right? I just take the stuff I threw away, flow it forward in time for a long time, and throw away anything that self-intersects. And the reason that this works is because this volume is integrable. This volume is integrable. So if I wait long enough, somehow, the factor is decreasing, right? So at each stage of this iteration procedure, I gain, say, a power of 2 or whatever. The volume is exponentially increasing, and I get sort of non-self-looping for as long as I like. Okay, so what that means is if you're contracting like this, you can again construct covers by this procedure where you flow, remove, start again, flow, and remove. So this is just, if you want, a quantitative version of the Poincaré recurrence theorem. Right? This is somehow what you have. And so now combining this with what I had before, I can define this mixed set where neither n plus and n minus are 0. And the story then becomes, if this intersection is empty, you get this logarithmic improvement. And I want to point out now that actually the previous statement, this splitting set, sort of leads you to believe that stable manifolds and unstable manifolds are the enemy somehow. And this one says that those actually are not the enemy, right? And there's some intermediate cases which is why, so if I go back, there's a reason that this is a surface, and that's because we don't know how to rule out the case that you're a direct sum of stable and unstable directions, but a non-trivial direct sum. Or at least, and in fact, that can happen, but it should happen in a small set. Right? It should happen in a small volume set, and that would be enough. So we actually conjecture this should be true in any dimension. Okay, and I want to just finish with a couple of other settings where you can do this, right? And so with John Toth, we sort of worked in the triaxial ellipsoid case. So I remind you, I'm just talking about the ellipsoid where there isn't any rotational symmetry, and there are some special points called umbilic points, and they have a nice dynamical property, which is that every geodesic going from here comes back to the same point at the same time. So every geodesic does like this, right? It's not closed, right? There are only 2 that are closed, but every one comes back at the same time. In particular, this is a uniformly maximally self-conjugate point. But nevertheless, because the structure of the dynamics here has a source sink structure, so there's contraction forward in time or backwards in time. And so by this contraction mechanism, you can again construct this sort of cover. And this is also an example where this type of behavior is actually sharp. Right? You can construct eigenfunctions where this logarithmic gain is saturated. Okay, and now one more dynamical situation where you can do this. If you have some integrable flow, right? So this is called the quantum spherical pendulum, I think. And so it represents a pendulum on this, I think a ball on the sphere, basically, trapped on the sphere. And here you can actually get small o of 1 over log h gains for eigenfunctions. And that's because you have much more control on the dynamics, right? They're not exponentially contracting or expanding. And so you can do Egorow's theorem for really very long times. And so this is certainly not optimal, right? You can push this further, right? Okay, so the story is that by understanding, so let me try to wrap up the 2 talks, right? The story is that by understanding concentration, you can get these nice estimates on eigenfunctions. You can put them together with Egorow's theorem and get some honest estimates which only depend on dynamical information near your submanifolds. Neither of us mentioned it, but you can use this to improve remainders in Weyl laws. If you want, you can get quantitative improvement in Weyl laws remainders by using these tools. And it all comes from the simple idea that concentration implies improved L infinity estimates. Right, that's sort of the story. Okay, so we hope that this geodesic beam technique will be useful in many other things, and so I will stop there and wish Richard a happy birthday.